We usually picture the pinnacle of modern technology as a humming, climate-controlled server room. It's an environment where every variable, temperature, humidity, power, is meticulously managed to protect fragile systems. But the physical world is messy, unpredictable, and often hostile to that level of engineering perfection. This gap between the lab and the field is becoming a liability as we shift from generative AI to agentic AI. We are no longer just asking models to summarize emails. We are authorizing them to take physical action. They are now in charge of steering wheels, engines, and industrial payloads. When you drop an AI model designed in a pristine lab into a 10-ton harvester in a muddy field during a storm, that pristine logic begins to fail. The vulnerabilities of the digital realm become immediately apparent in the dirt. For 15 years, we've operated under the assumption of ubiquitous connectivity, assuming the cloud will always be there, like gravity. That assumption is dangerous when you move from the digital world to a physical one, where signals are anything but guaranteed. In complex environments, external signals face a specific vulnerability called a multipath error. It's a phenomenon that exposes the danger of trusting any signal from the sky as absolute truth. This diagram shows the math in action. A GPS signal is just a radio wave. In an orchard or a shipping yard, that wave often bounces off a tree or a metal container before hitting the receiver. That bounce causes a microsecond delay, which the AI interprets as a spatial error, suddenly believing the machine is 30 feet away from its actual location. If the network lags while trying to resolve this, the machine operates blind. At 15 miles per hour, a 2-second latency spike means a 10-ton harvester travels 40 feet entirely unguided. Momentum doesn't pause for a buffering wheel. The machine simply continues until it hits an obstacle or a ditch. Scaling this up reveals the fragility of our infrastructure. Modern global agriculture and defense are orchestrated via these delicate, centralized digital threads. Entire fleets of tractors and irrigation grids are synchronized through servers thousands of miles away. Because these machines rely on a centralized orchestration layer to function, a severed fiber cable or a jammed signal can stop an entire operation. Without the ability to make local decisions, the machines simply wait for a command that isn't coming, turning a network glitch into a hard halt for food production and security. To build truly resilient systems, we have to teach machines to survive on their own in the dirt. This means cutting the cord to the cloud and moving intelligence directly onto the hardware. This requires a shift in how we program logic. Instead of a computer obeying sensor data implicitly, we have to build an algorithmic immune system that allows the machine to doubt its own inputs. The Kalman filter maintains a continuous mathematical model of the machine's state, tracking mass, velocity, and heading. When a bounced GPS signal claims sudden, impossible movement, the filter compares it to internal accelerometers, recognizes the data as physically improbable, and rejects it. By assigning a near-zero confidence score to that bad data, we are giving the AI the trait of localized skepticism. The machine identifies the anomaly, isolates it, and avoids acting on a hallucination. Usually, running complex models like these requires massive GPU clusters. This raises a major hardware hurdle. How do you run a sophisticated immune system on a ruggedized device bolted to a tractor in a field? The answer lies in the Model Context Protocol, or MCP. It's a framework that changes the way AI communicates with local sensors and tools. This comparison shows the difference. On the left, traditional AI wastes time and power pinging a distant server. On the right, MCP strips away the network bloat and creates a hyper-efficient closed loop directly on the motherboard. By removing the need for a network stack, compute overhead drops significantly. This allows powerful, quantized models to run natively on edge hardware, making decisions in a fraction of a millisecond without any external help. This localized architecture shifts operational sovereignty out of Silicon Valley server farms and back into the hands of operators. It allows for enterprise-grade intelligence in areas where the internet doesn't exist. Localized skepticism gives a machine the ability to degrade gracefully. It changes a catastrophic failure into a managed transition. When the machine recognizes corrupted GPS data, it doesn't just stop or veer off course.
It ignores the bad signal, relies on trusted local sensors like cameras or LiDAR, and brings itself to a controlled, safe halt. This technology is currently being tested through open-source pilot programs. Developers are being challenged to download the server, physically cut their Wi-Fi, and build agents that can navigate the physical world entirely offline. Engineering resilience is measured by how a system performs when the environment is working against it. High-performance intelligence isn't about how much data you can process in a perfect lab. It's about maintaining functionality in the dirt. But teaching one machine to doubt is only the beginning. Imagine a signal-jammed field filled with a swarm of autonomous tractors or drones, all operating without a cloud connection. Because each machine relies on its own local Kalman filter and internal sensors, every unit will form a slightly different mathematical truth about its location and the obstacles around it. Without a central cloud referee to tell them whose math is correct, these isolated machines must find a way to negotiate and cooperate. This shifts the challenge from individual resilience to collective negotiation, finding a shared truth while working entirely in the mud.